So again, like we said, these probabilities are actually mathematical equations, and they define a region in space where the orbitals are located. Um, so again, remember S subshells always have only one orbital, and the shape of that orbital is always spherical. I think I'll show you on the next slide, but it's just kind of like if there's the nucleus, but it's in 3 dimensions, so it's a sphere around the nucleus. The p subshell orbitals, and remember there's always 3 p's, they actually look like little dumbbells, and they each have a different direction. It's probably on the next slide, so I'll show you that when I get there. And then the d subshell orbitals, remember there are 5 d orbitals, are always a mix. They're kind of a mix of cloverleaf and dumbbell shapes, which I'll show you in a second. Okay, so here's the s orbital. So like I said, it's kind of a sphere. So my nucleus is here at the center, and then this is the region. And notice it's a little bit darker here, meaning the electron density is a little greater closer in, but this is like the 99% probability that the s electron will be in this region where that's the nucleus. It does get a little bit complicated. A 2s orbital is also a sphere, but it's just bigger, meaning it's a bigger region in space. So it could be that the electrons kind of can be in the same region, but they're kind of not really. So the s orbitals are spheres. The bigger the higher energy level have bigger spheres. So that's just another way of looking at it. So again, the nucleus is at the center. Here's the p orbitals. So there are, so they look, you can see here, they kind of look like dumbbells. So that's the region in space. That just represents the probability. And of course, it's more dense here. It's more likely to be here, but they can be anywhere in this dumbbell region. And since there's 3 of them, so this is showing the 3 axes. So if the nucleus is right here at the center, I can't really, like right there in the center, kind of there. So remember that there's 3 orbitals, and sometimes we'll call them 2px because one of them centered on the x-axis, 2py because it's centered on the y-axis, and then 2pz because it's centered on the z-axis. Now the 3p orbitals will look again just like this, but they'll be a little bit bigger, but they'll still be oriented on the x, y, and z axis. So if you see this little notation, just realize it's indicating 1 orbital out of the 3 possible orbitals. And then these are what the d orbitals look like. These happen to be the 3d orbitals, and we're just really not going to worry about them. I kind of remembered, so they're kind of, this video is kind of interesting if you want to see where they come from. It's kind of long, but anyway, I do want you to know the dumbbell shapes of the P and the spherical shapes of the S, and in general to realize that these kind of look like clover leaves, except for this one that kind of looks kind of like a weird, I don't know what you call it, but anyway, there's 5d orbitals, and again, they have different regions in space, different orientations. You can kind of put them together. I think those videos, if you look at those videos on the previous 2 slides separately, it kind of puts them all together and you can see them. So anyway, just to review one more time, because it's kind of a lot thrown at you, but I think once you get the whole picture, it's better. So again, N indicates which main shell I'm in. I'm in the first shell, the second shell, the third shell. N equals 1, 2, 3. L indicates the subshell. So if L equals 0, this is an S subshell. If L equals 1, it's a P subshell. If L equals 2, it's a D subshell. If L equals 3, it's an F subshell. Now, why is it SPDF? That's shrouded in history too. I think they originally meant something. I think the D stood for diffuse and the S stood for sharp or something. There was something when they were first learning about these things where these letters came from. And then after F, then they just go alphabetical. So it is, unfortunately, it could just be A, B, C, D, but no, they've got SPD, and that's just gone through history. Remember that there can be N subshells in any shell. So if n equals 1, there's only one subshell. It's the 1s subshell. If n equals 2, there are two subshells, 2s and 2p. If n equals 3, there are three subshells, 3s, 3p, 3d. So remember that that L can be anything up to n minus 1. So so on n equals 3, we've got the three subshells. N equals 4, we have the four subshells, and so forth. Remember that m sub L actually indicates how many orbitals there are in each subshell. So for any L, there are two L plus 1 values, meaning S has 1 orbital, P has 3 orbitals, D has 5 orbitals, F has 7 orbitals, G will have 9 orbitals, so forth. And then m sub S indicates the spin. It can either be plus 1/2 or minus 1/2. Now, because there are only two spins, this means that there can only be up to 2 electrons in any orbital. And we'll talk about that in a minute also. So this is, again, a little bit of a summary. It's kind of similar to the one I showed you earlier. So N is the shell. It could be 1, 2, 3, 4. Angular momentum quantum number can be anything between 0 up to n minus 1. And that indicates the subshell, which also tells me the shape of the orbital. And then the magnetic quantum number can be anything between negative L and positive L. And that tells us the orientation of the orbitals. And then the spin quantum number is actually sort of the intrinsic spinning of the electron. Just some more things that can help you with the summary. The total number of subshells in any shell is n. So whatever shell you're in, that's how many subshells you can have. The total number of orbitals in any shell, now keep that in mind, that's just for a shell, is n squared. So if you're in the first shell, you have 1 squared or 1 orbital, which happens to be the 1s. And then therefore 2 electrons. If you're in the second shell, you'll have 4 orbitals. Remember, so that's 1s and 3 p's for a total of 4. If you're in the third shell, you can have 9 orbitals. Remember, there's 1s, there's 3 p's, and there's 5 d's. So that's a total of 9. And if you're in the fourth shell, you will have 16 orbitals, 1s orbital, 3p orbitals, 5d orbitals, and 7 f orbitals. So that equals 16. And it'll just keep getting bigger and bigger and bigger. So whatever shell you're in, you square it, and that's how many orbitals you have. Now, how many electrons are in a shell? 2n squared, because there's 2 electrons in every orbital. So on the first shell, you can have 2 electrons. On the second shell, you can have 8 electrons. On the third shell, you can have 18 electrons. And on the fourth shell, you can have 32 electrons. And then therefore on the fifth shell, you can have 50 electrons, because 25, 2 times 25 is 50. So here's kind of what I just summarized. So again, on the first orbital, there's only one s. There's 4 orbitals on the second shell. There's 1 2s and 3 2p's. 1, 3, and 5, 1, 3, 5, 7, so forth. Yeah, so if we complete this, n equals 5. There's 25 orbitals. There can be 1, the 5s, there's 1. There's 3 5p's. There's 5 5d's. There's 7 5f's. And there's 9 5g's. So that's a total of 25, and that would mean 50 electrons. So we can keep going and going and going, and this is what's allowed. All right, so let's just do a few more examples. What kind of subshell do we have if n equals 5 and L equals 4? Well, obviously we're on the 5th shell, so it's a 5. And then what is L equal 4? Well, first of all, is it allowed? Yes, because L can be anything up to n minus 1. And let's just remember, L, if it's 0, it's S. People tend to forget that, and I do too sometimes. 0 is S, 1 is P, 2 is D, 3 is F. So 4 is a G. So this is a 5G subshell. How many orbitals and electrons are there in this subshell? All right, well, we know, and now, again, keep in mind that last page I told you, that was for the whole shell. So sometimes we can break it down into subshells. So on the 5G subshell, remember that if L equals 4, then we can have 2L plus 1. So that means 9. We can have 9 orbitals. Just on the 5G. We got through saying there's 25 orbitals overall on the 5th shell, but just in the 5G subshell, there is 9 orbitals. The other orbitals will come from other subshells. And then, so how many electrons are in this subshell? 18 electrons. All right, what do these set of quantum numbers indicate? N equals 4, that tells me I'm on the 4th shell. If L equals 2, I can look up here, 2 is a D subshell, so that tells me I'm in a D subshell. So it's a 4D electron. If M sub L equals -2, now let me go ahead and draw it. So if I'm on the 4D subshell, and we know D's always come in 5s. And just to kind of be complete here, since M sub L could be anything from -2 to 2, I'm just going to kind of go as we read left to right. I'm going to say that here's the -2 subshell, here's the -1 subshell, here's the 0 subshell, here's the 1, and here's the 2. So, you know, if the quantum number was 4, 2, -2, that means that box. If it was 4, 2, -1, that would be this box. 4, 2, 0 would be that box. So that's just kind of how we navigate it. And then finally, if M sub S is +1/2, that just indicates that the arrow is got a positive spin, and we represent that with an arrow up. So it's kind of like I'm pinpointing where that electron belongs. It belongs on the 4th shell, it belongs on the D subshell, it belongs in the first of the 5 possible orbitals, and it has a spin that's positive. So these 4 quantum numbers define this electron. If I was talking about a different electron, then what would change? Either if I was talking about, let's do the green. If I was talking, like green. If I was talking about an electron that went down, these first 3 would be the same, but this would be -1/2. So they would not all 4 be the same. If I was talking about an electron over here, then what would be different? The M sub L would be different. This would be +2 instead. So these 4 quantum numbers can help you pinpoint exactly. Sometimes, you know, I think of sort of a, I should have said this earlier probably, but I think about like, okay, the shells are kind of like maybe cities, like Abingdon, Damascus, Bristol, whatever. And then the subshells are, could be like streets. So maybe, you know, so city 1 only has 1 street. City 2 has 2 streets, S and P. City 3 has 3 streets, S, P, and D. Now, then there's more rules, like if I'm on S Street, no matter what city I'm on, S Street only has 1 house. P Street always has 3 houses. D Street always has 5 houses, and so forth. But if my city doesn't have a D, you know, if I'm in city 1, then I only have 1 street, 1 house on that street, but I can put 2 people in there. If I'm in city 2, then I have 2 streets. There's 1 house on 1 street, 3 houses on the next street, so I can have a total of 8 people, 2 in each house. So hopefully that makes sort of sense to you. All right, so just a little bit more. Now I'm just going through the answers, which I just did for you. So 5G subshell, how many orbitals? There's 9 orbitals, 18 electrons. What do those quantum numbers indicate? They indicate it's on the, the electron is in the first of the 5 4d subshells, and it has a positive spin. All right, just a few more examples. What kind of subshell do I have if n equals 6 and L equals 1? Well, n equals 6, obviously it's on the 6 shell. L equals 1 means a p, so it's a 6p. Doesn't matter that it's on the 6 shell. All that matters here is that if it is a p subshell, how many orbitals do I have? I have 3 orbitals. So I have a total of 6 electrons. No matter where that p is, like I said, if it's street p, no matter where it is, it's got 3 houses and it can hold 6 people. So if you want to think like that. Why are the following sets of quantum numbers not permissible? Okay, well, let's just go through them. So if n equals 3, no problem. If n equals 3, can L equal 2? Yes, because L can be anything up to n minus 1, which is 2. So L can equal 2. M sub L, remember the rule, M sub L can only be equal to negative L up to positive L. So it can only be negative 2, negative 1, 0, 1, and 2. So this is not correct. And negative 1/2 is fine, but this is not. We can't have a plus 3 orbital in a p subshell. D subshell, sorry, D subshell. See, I do it all the time. Okay, oh, I got those reversed. Okay, n equals 2, L equals 1. Sure, that's fine, because L can be anything up to n minus 1. Can M sub L equal negative 1/2 or negative 1? Sure, if L equals 1, M sub L can equal negative 1, 0, or 1. So that's fine. Can M sub S equal 3/2? No, of course not. We know that's wrong. Okay, what about this one? Can n equal 0? Well, first of all, n can't equal 0, so that's wrong. If n equals 0, L could not be 1, so that's wrong too. So they're all, well, that could be right. But anyway, and that could be right. But this is the first thing. You can't have an n equals 0. Finally, what are the set of quantum numbers for an electron in the 3s orbital with a negative spin? Okay, so in other words, what I want is I want to find the 4 quantum numbers that represent this electron. So let me kind of draw it. Well, I'm in the 3s. I mean, how many orbitals? You know, I'm in the first shell, the second shell. Now I'm in the third shell. This is the 3s subshell. How many orbitals are in a 3s subshell? There's only ever 1 orbital on the 3s subshell, and I'm talking about the negative spin. All right, so let's do, so what does the quantum number have to be? Well, if it's the 3s subshell, then n has to be 3, because n is just whatever shell I'm in. If I'm in an s subshell, that means L has to equal 0. Of course, L can equal 0, 1, or 2, but I'm specifically talking about a 3s subshell, so L has to be 0 for a 3s subshell. So n equals 3, L equals 0. Now, because there's only 1 orbital on an s, M sub L only has the option of being 0 for this. And then if I have a negative spin, then that means M sub S equals negative 1/2. So these 4 quantum numbers represent that electron in the third shell, the s subshell, the orbital, the 0 orbital, which is the only one, of course, and then the negative spin. So again, I hope that makes sense. I just went through these. Okay. While I'm at it, let me give you the quantum numbers for the 3p orbital. So let's just do the 3p orbital. So again, n has to equal 3 for all of them. So first of all, how many electrons are in the 3p subshell? 3p subshell will have, totally, will have 6 electrons. So I'm going to come up with 6 sets of quantum numbers that represent these 6 electrons. So n for all of them is going to be 3. Has to be, because they're all on the third shell. The L for all 6 of these electrons have to be 1, because S is 0, P is 1. So L is 1. Now here comes where the difference is. So if we have a 3p subshell, we have 3 orbitals, right? So m sub l can be -1, it can be 0, and it can be +1. Then m sub s can be 1/2. But since m sub s can also be -1/2, I can have these three again. It doesn't matter the order. You could have put -1, 1/2, -1, -1/2, 0, 1/2, 0. You could put them in any order, but these are the 6 electrons that will fill up the p orbital. So that's something else you can do.